This
So,
conference will now be
to start
recorded.
with, yesterday, as I said, we started discussing things with respect to the CAN. So, CAN is a communication protocol which represents controller area network, and this protocol was by the Robert Bosch company. So after the CAN, like the basic reason for introducing the CAN communication protocol was to make things automated. So they wanted to design an automatic device. They wanted to make things automated. So that is why they wanted to establish the communication between the two chips in an efficient manner. And Robert Bosch company introduced the CAN protocol. How it is made? No, see, this is not made automatic. Like they wanted to design an automatic device most of the times, and in the automatic devices there will be communication between two chips of two different boards. So there will be multiple communications between two chips of two different boards. And sometimes what happens is, let's say when I apply brake, if you take a car, so there might be multiple things to be taken care of. So speed has to be reduced. Then the lights. Okay, yes, the red lights, the back lights should be turned on. Then like certain things to be achieved. Give me a second. Okay, so we wanted so many things to be achieved, and there has to be the communication between two chips of two different boards. And you cannot rely only on a UART protocol. They wanted an efficient communication protocol to have communication done between two chips of two different boards. And also, you know, the advantage that this helps us do the multicasting also. So because of that, this protocol was introduced. And using this, they have designed so many automatic devices as well. Okay. All right. So coming to the CAN, we saw the introduction to the CAN. It's an asynchronous half duplex protocol. We have multi-master, multi-slave. We don't refer the devices as master and slave. We generally refer it as the nodes in case of CAN protocol. So you can have multiple devices in the network, and one device can actually transmit the data to multiple other devices in the network. Then we saw I'm sorry. Then we started with the basic concept. So we saw an example where every node should be made up of three important components: the controller, CAN controller, and the CAN transceiver. Some of the nodes may have controller and CAN controller built in. CAN transceiver should be added separately. And in some of the cases, you may have to add all three things separately. But you may come across a node which may have controller, and CAN transceiver built in on a same board. But we don't have such device yet. So later days, you may see such device which will have all three components present inside it. Then we saw the different versions. We saw the properties of the CAN protocol. So it gives priority to the messages. It guarantees the latency time. There is flexibility in the configuration, and you can do multicasting. And when the casting is happening, all of the devices are time synchronized. So there is a system-wide data consistency. You cannot doubt the data being received by all the devices. We have multiple masters, means multiple nodes can start transmitting the data at the same time. So there is error detection, error signaling, and automatic retransmission. So if any node is going to win the bus, whoever is not winning the bus is going to back out from the communication. But whatever data needs to be transmitted by another node will automatically get transmitted. So even if it is out of that particular network. Now, distinction between the temporary errors and permanent errors are made, and you can identify the failures of the nodes. And if the nodes are found to be defective again and again, so there is autonomous switching off of the nodes as well. So OSI model is the basic idea behind the CAN protocol also, but CAN has only three layers: application layer, data link layer, and the physical layer. Then coming to the frame formats, we have two types of frames. One is, two formats of frames. One is a standard frame, the other one is the extended frame. So 11 bits of identifier is available in the frame. You call it as a standard frame. 29 bits of identifier is available. You call it as an extended frame. Now there are four types of frames. So if you have a data to be transmitted, you transmit it with the help of data frame. If you have a data to be received, you are requesting for some data, you are going to transmit a remote frame. So if you have an error to be identified, a error frame gets transmitted. And to give a timestamp, to give a delay between the two frames, between the two data frames or two remote frames, or between a data and a remote frame, we will transmit a overload frame. Any doubts in these? Okay. Now understanding, if you understand data frame, remote frame is very similar to that. If you understand error frame, overload frame is also very similar to that. Yesterday we finished understanding a data frame. How many fields does a data frame have? How many fields the data frame has? So it is going to have how many fields? Yes, so it is going to have 7 fields. A data frame has 7 fields. The very first field is the start of the frame field. It is a single bit which is always 0. Then you have arbitration field which is either of 12 bits or 32 bits. The control field is of 6 bits. Data field is of 0 to 64 bits, or I can say 0 to 8 bytes. Then CRC field is cyclic redundancy check, which is of 16 bits. Acknowledgement field is of 2 bits. And end of the frame field is of 7 bits. So we saw what and all happens in the data frame. So first, if you go with the arbitration field, once the start of the frame is received, all the nodes in the network pay attention and they will be expecting the identifier. So the node in the network, whoever is transmitting, will first transmit 11 bits of identifier and 1 bit of intention. After this, there will be an identifier flag bit which will tell whether you are going to receive a 11 bits of identifier or 29 bits of identifier. So if it is 0, it represents there is only 11 bits of identifier and it's a standard data frame you are going to receive. And if it is ID being 1, then it represents you are going to receive an extended data frame, means you will have 29 bits of identifier. Now, if it is only 11 bits of identifier, then R0 will be reserved bit. DLC3 to DLC0 represents the size of the data field. Then data field, cyclic redundancy check field, acknowledgement field, and end of the frame will be received. But in extended data frame, after knowing ID is 1, that is after knowing that you are going to receive an extended data frame, so whatever RTR bit is there, the the remote transmit request, so that will be changed to SRR. So that is substitute remote request. So it will be changed to SRR and it is always made a 1. Now that 11 bits of identifiers are received, another 18 bits of identifier will be collected later, which is called as extended identifier. Then the actual RTR will be received. Then control field, the 6 bits, R1 is the reserved bit, R0 is another reserved bit, DLC3 to DLC0 will be taken, and we are going to have the data field, CRC field, acknowledgement field, and the end of the frame field. So yesterday we saw all of these fields in detail: the control field, arbitration field, then data field, CRC field, acknowledgement field, and also the end of the frame field. It is representing 7 ones. Any doubts in the fields of the data frame? Any doubts? Okay. Now, when are you going to transmit a remote frame? When are you going to transmit a remote frame? So you transmit a data frame if you have any data to be transmitted. So when are you going to transmit a remote frame? Wireless? No. So I just said about it. So if you have any data to be transmitted, you transmit a data frame. Yes. Whenever you are going to request for some data, you want to receive some data, you are going to request with the help of a remote frame. Okay. You request the other device to send the data by transmitting a remote frame. Now, this remote frame also has the same fields as that of a data frame. So data frame has 7 fields. Now, out of the 7 fields, only one field is absent in the remote frame. Can you guess which one is that? So, out of the 7 fields, only one field is absent in the remote frame. Yes, so it's the data field. So, you are not transmitting any data. You are in fact requesting for a data. So, data frame is in fact absent in case of remote frame. Rest all other things remains the same. So remote frame is made up of 6 fields. First one is start of the frame field. Second one is the arbitration field. Then control field, cyclic redundancy check field, acknowledgement field, end of the frame field. Now, yes, start of the frame field is again 1 bit which represents 0. Arbitration field is of the same 12 bits or 32 bits. Control field is also same. It is made up of 6 bits. TRC field is also same, which is made up of 16 bits. Acknowledgement field is made up of 2 bits. And end of the frame field is also made up of 7 bits. Now the only difference is data field is absent here. And when it comes to the arbitration field, you have a bit called RTR. So what do you mean by the RTR bit? When are we going to make use of RTR bit? When are we going to make use of RTR bit? Okay, so when two buses transmit at the same time, no, read or write, correct. So whenever you have to specify the intention along with the 11 or 29 bits of identifier, you may also have to specify the intention. So whether you are going for the purpose of reading or for the purpose of writing. So earlier you were transmitting a data frame, you had a data to be transmitted. So RTR was representing what? Read or write? In the data frame, RTR was representing the write operation, which is nothing but 0. And this time, am I going to write any data? When I transmit a remote frame, no, I'm not going to transmit any data. So I'm not going to write. In fact, I'm going to read the data. So in order to read, the RTR bit should always be a 1. Recessive means it has to be a 1. Okay. So RTR field should always be a 1. So that is remote frame. Okay. So we have different frames. Data frame and remote frame are very similar to each other. In data frame, you don't have a field called, you have 7 fields. In the remote frame, you have only 6 fields. The data field is absent here. And another difference is RTR is written with the value 1 here. Okay. Next, when are we going to transmit an error frame? Or generally, we don't transmit any error frame. So error frame is generally transmitted by the node itself if there is any error occurring. So you being the programmer need not transmit an error frame. Now, what does an error contain or an error flag contain? It has 2 fields. One is a error field, the other one is error delimiter. Okay. So we have 2 fields. One is error flag, the other one is error delimiter. Okay. Now, the first field is given by the superposition of error flags contributed from different nodes. The second field is the error delimiter. So first I have error flag, which is a contribution of multiple other fields. And we have error delimiter, which is to represent that it is a error frame. Now, error flag can either be active error flag or passive error flag. So, we have two types of error flags, active error flag and passive error flag. Now, when it comes to the active error flag, it is going to consist of 6 consecutive dominant bits. Now, what do you mean by dominant bits? Dominant bits are always 0, recessive bits are always 1. Actually, whenever you come to the CAN communication protocol, we have a mechanism of saying that the device, whether it is in the active state or it is in the passive state. Okay. So any device you are going to take can either be in the active state or it is in the passive state. Now, if the device is in the active state, then the active error flag is going to consist of 6 consecutive dominant bits. And if your device is in the passive state, the passive error flag is going to have 6 consecutive recessive bits. Now assume yours is a active state. So my error flag will have 6 zeros, and when it comes to the delimiter, we have 8 recessive bits. So 8 ones. Okay. If your device is in the active state, so error frame is going to have 6 zeros and 8 ones. Similarly, if your device is in the passive state, error frame is going to have 6 ones and also 8 ones. Okay, so that is nothing but the error flag which gets transmitted automatically if there is an error happening. So error frame has two fields, error flag and the delimiter flag. An error flag is depending on the state of the device, which is either in the active state or in the passive state. Now, how will you decide if the device is in the active state or the passive state? I'll show with an example going ahead. But remember, the error frame gets transmitted if there is an error happening. Okay. Then apart from this, we also have something called as overload frame, a frame which will be used when you have to give the space between the two frames. Okay. So it is going to consist of two fields again. One is overload flag and the other one is overload delimiter. So overload frame is made up of overload flag and overload delimiter. Now, 3 different overload condition leads to the transmission of the overload frame. Now, internal condition of a receiver require a delay of the next data frame or the remote frame. So, first reason when you need a overload frame is, let's say the receiver needs a delay between the two data frames or between the two remote frames or between a data and a remote frame. You are going to transmit a overload frame. At least one node detects a dominant bit during the intermission. So while the communication is happening, okay, so assume one of the node detects a dominant bit. Dominant bit means it is a 0. Okay, so dominant bit means 0. So if any of the line is detecting 0, okay, that means the bus is actually been busy. Okay. Now, if the bus is been busy, that means there is some communication happening. So, whatever node is in the network should be waiting for the next data to be received. So, to indicate that there will be a overload frame being transmitted in that particular network. A CAN node samples a dominant bit at the 8th bit of a error delimiter or a overload delimiter. So one more reason is if there is a 0 seen, okay, if the CAN node identifies a 0 at the 8th bit of an error delimiter or a overload delimiter. So remember, it is going to say that there is a need of overload frame. Okay, in these 3 scenarios, so there is a need of overload frame. Now, overload frame again is going to have 2 sections. One is overload flag, the other one is overload delimiter. Overload flag consists of 6 dominating bits and overload delimiter consists of 8 recessive bits. So in fact, overload frame is always fixed. So it is going to have 6 dominating bits, that is 6 zeros and 8 ones. Okay, so that's a overload frame. Understood overload frame and an error frame? There's nothing different in this. You just have to see how the frame format looks like. Okay, now proceeding ahead. So we discussed all the fields. Error handling. Now, some of the times the errors can be detected, some of the times the errors can be signaled. It's just like error frame, how processor will understand it's a overload. See, error frame can be transmitted anytime. So while the data transmission is happening, in between a data, let's say half of the data frame is being received, you can transmit an error frame. So like the remote frame is not completely received, you can get a error frame. So error frames occurrence can be anywhere. But when it is a overload frame, so overload frame is always after a data frame is received or a remote frame is received. So in between, you are not, like, while the communication is happening, while the data frame is being transmitted, you will never transmit a overload frame. Okay. Did you get this? Okay. So as I said, when it comes to the CAN communication protocol, so remember we can have some errors detected. Okay, we can have the errors detected. Some of the errors just gets detected. Some of the errors will also be signaled that this is an error, you may have to check it. Okay, some of the errors will always be detected and some of the errors will always be uh, significance of a overload frame. So as I said, if you want to give a delay between the two data frames, you want, like, let's say the receiver is not able to receive continuous data frames one after the other or continuous remote frames one after the other. You want to create a delay between the two important frames, you are going to transmit a overload frame. It is to waste some time between the two data transmission. Okay, fine. So proceeding ahead, as I said, some of the errors can be detected and some of the errors may have to be signaled. So there are only two errors which gets detected. One is a bit error, the other one is a stuff error. Now bit error means it's an error which happens if there is a random bit between the two fields. So between a error, like let's say if you take a data frame between the two fields, let's say CRC field and acknowledgement field, or data frame and control field and data field. So that way, between the two fields, if there is any extra bit being added, so that represents a bit error which gets detected. Okay, it will not be signaled, it gets detected. So you may have to keep checking if the bit error has occurred or not. Now, stuff error is, we have something called as stuffing rule to be followed in the CAN protocol. Now, assume I have 6 zeros to be transmitted as a data. Okay, so I want 6 zeros to be transmitted as a data. So in that case, I cannot transmit this 6 zero as it is, because 6 zeros represent a error flag in case of a active device. And similarly, if I have 6 ones to be transmitted, 6 ones represent a error flag in case of passive device. Now in that case, as you know, I cannot transmit the data as it is. We have to follow a stuffing rule. Now according to the stuff rule, So first you have to transmit 5 bits of data. Then you have to toggle the bit. Then you have to transmit the 6th bit. Similarly, if I have to transmit 6 once, I have to first transmit 5 once. Then I have to toggle the bit. Then I have to transmit the 6th bit. So that is stuffing rule. Now, if you don't follow the stuffing rule, it is possible that it creates an error called as the stuff error. Okay. Now, if it is an error flag, then there is no problem. Now, assume you see 6 continuous zeros or 6 continuous ones in a data frame in the data field, then it is going to show you a error called as the stuff error. Okay. So, we have something called as stuffing rule which needs to be followed all the time. So, if that is not managed, you are going to end up getting a stuff error seen. Okay. And that again will be detected. It will not be signaled. So, you may have to keep an eye and keep checking if there is any stuff rule happening. I mean, stuff error happening. Then some of the errors get signaled. One such error is CRC error. So CRC is cyclic redundancy check. There will be a sequence generated whenever you have got a, let's say, assume there is a sequence generated when you are supposed to transmit a data. So you have a data to be transmitted and accordingly a sequence is going to get generated. Okay. Now, the receiver also, once the data is received, the receiver also generates the CRC sequence depending on the data being received. Now, the receiver compares the CRC sequence it has generated with the CRC sequence which has been transmitted. And if the CRC field is a match, then it is fine. And if CRC field is not a match, it is going to throw a error. And that error will be signaled as well. Then we have form error. That means after every field, we have the dedicated field to be present. After start of the frame field, you should have arbitration field. Then you should have control field, data field, then cyclic redundancy check field. Then you have acknowledgement field, end of the frame field. Now, if this is not maintained properly, if the frame form is not maintained properly, it leads to a form error. And we also have acknowledgement error, which happens if the device is not acknowledging. So if the receiver is not acknowledging the data being received, or if the transmitter is not acknowledging the data which is being transmitted, it leads to an acknowledgement error. Okay. So these 3 errors will be signaled if it is occurring. CRC error, form error, acknowledgement error. Okay. And one last thing, when it comes to the CAN communication protocol, so we have something called as fault confinement. So how are you going to decide a node as an active node, a passive node, or it is in the bus off state? So any node in the network can be of any of the 3 things. So it can either be in the active state or in the passive state or in the bus off state. What happens in signaling and not in detection? See, in signaling is it is, let's say it is like an interrupt. So when that particular error is identified, there will be a signal given. It's like an interrupt. But when it comes to the error detection, error will be identified and a bit will be set. So you have to continuously monitor that bit. So you have to go with the concept of polling in that case. Okay. All right. So if you take a node in the CAN protocol, it can either be in the active state, or it can be in the passive state, or it can be in the bus off state. So there are 3 states in which a node can be present. Now according to this, you consider the device is in the active state or passive state or bus off state depending on the performance of that device or performance of that node. Now, whenever there is a node, there will be a tracker associated to that node which counts the number of errors it has made. And the errors are distinguished between transmitting and receiving. Now, if a node is making any error while the data is transmitted, it is counted under transmitting error. And if the node is making any errors while the data is being received, it is considered as receiving error. Now we have transmit error counter, receive error counter. Now assume there is a node which made an error while the data is transmitted. Transmit error counter will be updated. Now if the device is making any error while the data is being received, receive error counter will be updated. Similarly, one more error, one more addition to that counter. So one more error, one more addition to that counter. So this way, every time an error occurs, it will be counted under transmit error counter and receive error counter. But not just this, if the errors are rectified, this will also be reduced. So if let's say one error is rectified, I can say -1. One more error is rectified, I can say -1 in the receiver. So errors, like if the errors are not rectified, it will be in the track here. If the errors are rectified, so I'm going to get it reduced also. Now, if the transmit error counter or receive error counter is less than 127, we call it as the device is in the active state. So transmit error counter or receive error counter is less than 127. Okay. So we call it as not 127, in fact 128. So if it is less than 128, we call it as active state. Now if it is greater than 127, that means, so from 128, if it is greater than 127, we call it as the device is in the passive state. Okay. So the device is in the active state, the device is in the passive state. So active state, if transmit error counter and receive error counter, or in fact transmit error counter or receive error counter is lesser than 128, the device is in the active state. And if it is greater than 127 and lesser than 255, then we call it as passive state. So that is also fine. But if the transmit error counter or receive error counter is greater than 255, so we say the node is not qualified to be in the network and we put it under the bus off state. Okay. Now if the device is in the bus off state and if it has to come back to the active state, there are two ways. One is you have to reset the CAN controller, or you have to transmit 11 consecutive recessive bits for 128 times in the network. So if the device is in the bus off state and it has to be brought to the active state, you can either reset a CAN controller or you have to transmit 11 ones for 128 times. So in that case, the device will be brought to the active state. Okay. So remember, transmitting error counter, receiving error counter will keep a track of the errors which has been occurring. Okay. So I'll write it down here. Okay. So if transmit error counter and receive error counter is less than 128. Okay. So that means 0 to 127. So then the device is said to be in the active state. Okay. So the device is said to be in the active state. Similarly, if the transmit error counter and receive error counter is greater than 127. Okay, is greater, here I would say lesser. So greater than 127 and lesser than 256, less than 256. That means 128 to 255. You call the device as passive state. Okay, so this is passive state. Okay, then if the transmit error counter or receive error counter, in fact I should have said or, so transmit error counter, let me change here, or, so this is also or, and this one is also or. Okay, so transmit error counter or receive error counter is greater than 255. Okay, so then you call it as bus off state. Now to bring the device from the bus off state to the, let's say, can controller reset or 128 off. So when the device is in the bus off state, to bring it to the active state, you have to transmit 11 ones for 128 times, or you have to reset the CAN controller. Got it? So by any of two options, how errors will be reduced. So it's like the controller, it's the CAN controller which will keep the track of transmitter error and receiver error. So once you do it, okay, so it is like a punishment. So once you do that, once you take that punishment, by default, transmit error counter and receive error counter will be reset to 0. So in that case, it will be put under the active state. Got it? Okay. And this completes the CAN communication protocol, and this in fact completes your module as well. Any doubts? And as I said, our microcontroller actually supports CAN. So you can have a communication done with our microcontroller. But as I said, if you have to communicate with another device, so you need another device which supports the CAN protocol from another board. Okay. And also, you also need a CAN transceiver. Okay, so CAN transceiver should be there in order to achieve this communication protocol. And also you need this twisted pair cable concept as a application. So because we are working remotely, we don't have that option. We don't have an application which works as a CAN transceiver. We don't have an application which supports CAN controller. In fact, I can try establishing communication between two PIC microcontrollers taking two different boards. Okay. So, but the problem is, yes, the advantage of CAN is it has a twisted pair cable and it is very compulsory to achieve it. And again, we don't have a simulator for us to help this communication to happen. So we don't have it in the software side, which is why we don't have a programming part. Okay. So if you have any other hardware, then it's like you can try establishing the communication. So even in the offline mode, we will take only the two UART and I2C communication protocol. So CAN is like we don't take it on a regular basis. We just show what is CAN, how does a CAN transceiver look. So what is a twisted pair cable. So achieving the communication between two devices, buying the CAN transceiver and all is quite challenging. Okay. So having the basic ideology is sufficient. This is again asynchronous communication protocol. You already have a knowledge of UART, which is again asynchronous communication protocol. The only challenge here is the twisted pair cable. Apart from that, there is no other difference. And even you don't work with the twisted pair cable directly. What you say is digital 0 or 1 itself. It's the CAN transceiver who transmits the data in an analog way. It's the CAN transceiver who accepts the analog data and converts it into a digital value. So it's the task of the CAN transceiver which you don't have to do, and it gets identified automatically. Okay. All right. So this completes your module. Have you got any doubts? And in fact, we have to start with the project. Can I start it today? Everybody? So I just have to give an introduction. Okay, we'll do one thing. I thought it will take only 20 minutes, but 1 hour session has got over. I may not able to give the requirements in a single hour now. So we'll do one thing. Let's like do it freshly in tomorrow's class. So we will start with the project, and if time permits, we will also start the coding part of the project in tomorrow's class. Okay. So that means whatever we are going to use in our project, so it involves everything we have discussed in our class. So please make sure you're giving a quick revision for all the topics before you come for the next class. Okay. So we are going to involve multiple peripherals into a single project. So you please make sure you are coming for the class with a quick revision. Okay. Fine. So please have your attendance before quitting. Which protocol we use? So we use both UART and I2C because we have coding for both. So we are going to make use of both. Okay. So here is the QR. Please have your attendance marked and quit the session. Thank you all.